finding a drug that tackles the cause of FSHD. That's how you might describe what we're doing. It's a common way of saying what we're doing at Facio Therapies. We're finding a drug that tackles the cause of FSHD. Only we're not. We're not finding a drug that tackles the cause of FSHD. In fact, we don't even try to find that kind of drug. The thing is that a drug that tackles the cause of FSHD does not exist. And you can't find something that does not exist. A drug that tackles the cause of FSHD has to be designed. It has to be fit for purpose. And that's what I'm going to talk about today. The progress that we are making to design a drug that tackles the cause of FSHD that's fit for that purpose. But first, let me take you back to where we were last year, because we were here last year as well, as you may recall. Last year we talked about what you need to do, the kind of journey, if you will, that we need to make in order to arrive at that point, let's say a pill that tackles the cause of FSHD. You can't just make a pill and throw it onto the market. You need approval for that. And in order to get approval, you need to conduct clinical trials. And in those trials, you need to prove that the drug is safe and that it confers clinical benefit, that it improves the symptoms, or in this case particularly, that it stops the progression of FSHD. You have to prove that in clinical trials. What do you need in order to perform clinical trials? A couple of things. You certainly need tools to measure the effect of your drug. If you don't have those tools, if you put a drug out there without the ability to objectively say what it does and does not do, then effectively you're blind. So you need those tools. But you also need something else, because in fact you can't just start clinical trials either. You need approval for that as well. And one of the things that you need to show, there are many things, but one of the things you need to show is that your drug candidate performs well in an appropriate animal model. So you need those animal models as well, and you need to produce that data. And in order to produce that data, obviously, you need a compound, a drug candidate. And in the case of FSHD, as of course you all know, that is a compound that represses the production of the toxic protein DUX4. And then you need to find a way to actually discover that drug, and that means that you need a tool, a cell-based tool, in which you can test many, many compounds for their ability to repress DUX4. That's the journey that you need to make in principle. It's a little bit more complicated than that, but that's the journey in principle. So you move from relatively simple systems, cultured cells, to more complicated systems, animals, and then into the most complicated system of all, human beings. So do we have a system that can, in which we can test compounds for their ability to repress DUX4? Yes, we do. We are, in fact, still the only company in the field with a system that allows to quantify two things. Yes, lowering DUX4 levels, but also the effect that a compound may or may not have on the formation of muscle cells. And that's important because as you can see here on the screen, the system is based on a culture of primary cells. Those are patient-derived muscle cells that are unadulterated, so as close as possible to the real thing, if you see what I mean. And those cells are then allowed to grow from immature cells to mature cells. And DUX4 expression, DUX4 production is concentrated in those mature cells. So it is important to see if a compound that you put into that system has an effect on the formation of those mature cells. That's something that you would like to exclude, we anyway, also because that formation of muscle cells in this system is not unlike the process by which in a real body muscle cells are repaired and formed anew. So that's a system that we have, and we are still the only company that has that system. Do we have compounds coming out of that system that have promising properties? Yes, we do. We found, as the first company in the field, a completely novel mechanism by which DUX4 is repressed. And that mechanism is called CK1 inhibition, and the name simply says that the compounds that we are now concentrating our efforts on inhibit the activity of an enzyme that is called CK1. And these compounds do exactly what they are supposed to do. I won't go into the details of those graphs, but you can just concentrate on the blue line at the top and the green line at the bottom. What you want to see is that the blue line goes up, because that is the level of DUX4 repression, and you want the green line to stay flat, because that indicates that the compound, while repressing DUX4, has no effect on the formation of mature muscle cells. So we have CK1 inhibitors that repress DUX4 even up to 100% in this system, while leaving the formation of muscle cells intact. Do we have an animal model in which we have shown that these compounds work in principle? Yes, we do. It's a mouse-based model in which we have engrafted both human FSHD affected cells and healthy human cells. And you can see here in this picture on the left that the CK1 inhibitor does what it's supposed to do in that system as well. It reduces the level of DUX4 compared to placebo. And we checked that against a number of genes that are downstream of DUX4. DUX4 has, as you may recall, an effect on dozens, if not hundreds, of genes down the road, which ultimately leads to the muscle wasting that you see in FSHD. And just to check if the compound reduces DUX4 expression, it should also reduce the level of target gene expression, and in fact it does. So what we have here is a demonstration in principle that if you feed a CK1 inhibitor orally, so through the mouth, to this animal, it results in the significant repression of DUX4. So we have that as well. Do we have work going on tools to measure the effect of therapeutic compounds or drug candidates in human beings? Yes, we're also working on that. We are the first company to have conducted a study that tries to find out if real-world data can be used in a clinical setting. Why? Well, real-world data are measured by digital tools. In this case, it's a smart watch and an app, a smartphone app. And we have recruited or enrolled 38 people with FSHD and 20 healthy people, and followed them for 6 weeks using this app and the smartwatch. Why is that interesting? Well, the thing is that in a classical clinical study, you measure things every once in a while, because you have to puncture blood, you have to analyze that, you have to take biopsies. So it's discontinuous. There are just a few moments during those clinical trials in which you could actually see what's going on. This is continuous. So in principle, this has the capacity, the ability to produce markers, tools, biomarkers if you will, that are much more sensitive to small changes. And that is probably very important in FSHD because, as of course you know, it is a slowly progressing disease. And if you could use this kind of technology to pick up small, significant changes that prove to be significant down the road, that will be interesting. So that's why we conducted this study last year. And the two big questions were, first of all, can we define some sort of feature, some sort of digital feature coming out of this study that correlates to disease severity? That's what you want to see. And of course, the second question is this technology able to distinguish healthy people from people with FSHD? Starting with that last question, yes, that is clearly the case. This technology is able to sharply distinguish people with FSHD from healthy people with a high degree of reliability. But then, moving on to the first question, these are results, by the way, that have not been published yet. They will be published next month, so it's a sneak preview. And here you see one example of what this technology is able to do. We try to correlate the enormous stream of digital data that comes out of this study to a functionality test, which is called the timed up and go test, which basically is a test by which you see how much time it takes for a person with FSHD, for example, to stand up from a chair, walk a small distance, walk back, and sit down again. That's a functionality measure, not total, of course, but a functionality measure. And here you see that there is, in fact, a very good correlation between a certain subset of digital data and that timed up and go test. And interestingly, you also see here that this also relates to social behavior. This, you can't see it here on the split screen, but this says actually app use, so the use of apps, which is an aspect of social behavior. And that's also one of the interesting things of this technology. We all know that FSHD has a big impact on social life as well, and this is a way to quantify that, to make that objective. This was just an exploratory study, it's a snapshot really. So the next step would be to validate this over time in what is called a longitudinal study. So that's where we are. We've ticked a number of boxes. And now the question is, then what? So the big thing here is that we have shown in a relevant animal model that the kind of compound that we have discovered works to the extent that it represses DUX4. And now the big question becomes, how do you translate that significant finding into an actual drug that has the desired effect on humans? Well, let's focus on that. This is the question. How do we get to a drug that tackles FSHD in human beings? Well, one way to understand that is to see what happens if you feed a drug, an oral drug, let's say a pill, to a human being. And this is what happens, basically. There's a drug, you swallow it, it reaches the stomach, gets into the small intestine, passes through the liver, enters the general circulation, bloodstream, reaches muscle, enters the muscle cell, binds to CK1, at least in our case, represses DUX4, and bob's your uncle. That's it. Now you would expect the body to, I would almost say, appreciate that you try to aid it, because obviously the body itself is not able to take care of FSHD. That's why we give it a pill, to help it. The thing, however, is that the body does not do that. And that's because the body doesn't think. Well, we think here, but the body itself only reacts to chemical signals. And if you feed a pill to someone with FSHD, the body gets a chemical signal, and that chemical signal allows the body to identify the compound for what it is, an alien compound. It's a foreign compound. So the body puts up a whole series of mechanisms to try to get rid of the therapeutic drug. So this is what happens. The body strikes back. Now let's see what that means. So again, you have the drug, it's swallowed, reaches the stomach. First attack by the body because the stomach, of course, is a heavily acid environment and is in fact capable of destroying certain drugs. For example, you cannot take insulin by mouth because it's destroyed in the stomach. The other end of the spectrum, even if the drug does survive the stomach, it may cause damage to the stomach lining. But let's move on. It gets into the small intestine, and from the small intestine it has to enter the bloodstream. That's another barrier, because then the drug needs to pass the membrane that separates the intestine from the bloodstream, and that's a fatty layer. So the properties of the compound need to be such that it is able to pass through that fatty layer. Not all compounds are able to do that. Moving on, the drug passes through the liver. And this is an occasion where the body starts rolling out the big guns. Because the liver is designed to break down things. And it attacks, if you will, our drug as well. It transforms it into something else. It's a metabolic process. So it effectively robs the drug of its therapeutic identity and changes it into something that's not active. And that's eliminated from the body through the kidneys, for example, or through feces, or through bile. Again, at the other end of the spectrum, if a drug stays too long in the liver, or gets accumulated in the liver, because this is not a single passage, of course. The compounds that survive this attack will end up in the bloodstream, and therefore there are multiple passages to the liver. And yes, there are drugs that naturally accumulate in the liver. So-called antisense compounds, for example, do that. And that's a problem, certainly in the case of FSHD, where any therapy will be chronic. Moving on, the compounds that survive the attack by the liver enter the general circulation, and there the body has another trick, which is protein binding. One of the most, if not the most ubiquitous protein in blood is called albumin, and albumin can bind stuff to it, compounds to it. And when that happens, your drug is lost, because it's no longer available to do what it's supposed to do. The compounds that survive that as well ultimately reach the muscle. Well, that's to say, because they are in the general circulation, they will reach other tissues as well. And there, they may cause toxic effects. And if that doesn't happen, then at the very least, the compounds will also pass through the kidneys, which of course are designed to eliminate stuff. So there you lose drugs as well. And again, you can have the same effect there as in the liver. Certain compounds, again, antisense compounds, for example, naturally build up in the kidneys and cause long-term toxicity there as well, which is another problem. Okay. Compounds that reach muscle should also have the ability to enter the muscle cells, because DUX4 is on the inside of muscle cells, just like CK1. And that means they have to have the ability to actually get in there. And there are two barriers. The same kind of membrane barrier that we talked about with the small intestine, because muscle cells also have a fatty membrane, so the compound must be able to move through that membrane. But once on the inside, which is watery, it has to have the right properties to be active in that environment as well. And these are opposing criteria, because fat and water don't mix. Then finally, the compound is on the inside of the cell, seeks out the CK1 inhibitor, which is on the watery inside, binds to it, and there you go. That is to say, If after all these insults that the body launches on your drug, you still have enough left on the inside of a muscle cell to get an appreciable effect. If the ultimate concentration is too low, then you will not have an appreciable, an observable effect in people with FSHD. And you could say, well, okay, if that's the case, I'll just bump up the dose. But you can see the downside of that as well. That increases the risk of toxicity and side effects. So that's not a simple problem. It gets more complicated than that because there is not a straight line from CK1 to DUX4. There is a line, yes, but it's not a straight line. And it's certainly not the only line that CK1 is involved in because proteins and enzymes in our body act in networks. That's why our body is so efficient. But it also means that once a compound binds to CK1, there is at least a likelihood that that effect will ripple through the network and cause other effects as well. And that may cause side effects that you don't want to see. So, you have all sorts of red flags that the body pulls up, and you have to take care of these challenges, all of them. You can't ignore any of them. You have to take care of all of them in order to end up with a drug that is safe and efficacious, has the desired effect, the observable effect ultimately on someone with FSHD. So that's quite a challenge that the body puts up by striking back. How do you deal with that? By tinkering. You might say that the body puts up chemical warfare against your compound, your drug. Well, two can play at that game. We can do that as well. This is a 3D representation from a molecule. You see it from the bottom a little bit. It's an actual molecule, as a matter of fact. It's not a CK1 inhibitor. It's not one of our molecules, but it is a real molecule. And this, in fact, for me is the highlight of this presentation because I was trained as a chemist. And I've been working for years to get to this occasion where I can finally talk a bit about chemistry, but only a bit, only a bit. There is, just to make this a bit more exciting for you, there's $100 from my very own pocket for anyone who can tell me what this molecule is, the identity of this molecule. Of course, if you guess wrong, you have to pay me $100. And that's why each and every one of you is most cordially invited to have a go, all right? So while you think about that, one thing a chemist will immediately see is that this molecule should be able to pass through a membrane, because the left part of the molecule with the black and the grayish balls, black is carbon, the grayish balls are hydrogen, likes fat. The right part, which has black and gray but also red, red being oxygen, likes water. So you can see that this molecule should be able to move through the membrane, dragging the water-liking part with it, and then once on the inside, the water-liking part takes over and allows that compound to be active on the inside of the cell. Just to illustrate one of these many criteria that a compound has to satisfy in order to qualify as a drug. But of course, that's not all. Suppose, for example, that you find that this molecule, if this would be a candidate for FSHD, is not potent enough, does not bind strongly enough to CK1. That means that you have to make a chemical change to this compound. Suppose you do that, and you test it again, and the potency is improved. Well done. Does it mean you can move on simply to the next criterion that you have to fulfill? Well, actually, no. because you can feel intuitively, I would almost say, that any change that you make to this molecule changes its properties and therefore may also have effects that you did not intend. For example, it might mean that a positive change that you bring about in this molecule makes it more prone to, let's say, transformation in the liver, which is something that you don't want. In other words, the changes that you make in order to make it better have to be tested each time. You have to move it through the cycle each time. So this is not a linear process. It's not like you have, 5 boxes or 15 boxes and you tick, 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 and you're done. No, you have to move it through. It's not linear, it's a spiral moving up. That's what you're doing. And that's what we are doing right now. Not just with one compound, with dozens of compounds at the same time that move through these spirals, each with their own spiral, because these spirals, of course, are not the same. And that's why we have 30 odd people working for us right now. Yes, as a company, we're small. We have a small core team, but there are many more people work with us at our drug discovery partner, Evotech, for example, but also at other places to execute our R&D program. So this is pretty complicated. It's a lot of work. And it gets even worse because there's one thing I did not yet mention, which is that this compound, which is intended to be a drug, must also be manufactured at commercial scale. So just suppose you forget about that, interested as you are in this chemical warfare exercise, and you end up with a compound that does everything that you want to do, and then you find out that in order to manufacture it, you have to go through a process of 15 steps, each with a yield of 10%, which means that you still have nothing. You still don't have a drug then. So that's also something that you have to keep in mind, just like stability at room temperature, for example, or sensitivity to light, very mundane things. But that's also what you need to keep in the back of your mind, because you're working on not just an interesting molecule, it has to become a drug. So, wow, this is some puzzle that you have to solve. It's complicated, yes, but this kind of complexity, you have to realize, is not specific to FSHD. You always have to face these or similar issues. Whatever you try, for whatever disease, it's always the same story. You have to go through this process. Is it doable? Yeah, it's doable. Particularly because, as Bill mentioned in the beginning, we are working with a kind of compounds that are known as small molecules. And the small molecules are pretty much the oldest trick in the pharmaceutical book. There is a huge body of knowledge on what you can do to tinker small molecules in order to make them work. Where are we now? Well, the easiest way for me to explain that is to tell you where we are going. This is where we are going. The next big thing for us is the selection of a collection of compounds that we can take into preclinical trials. And in order to do that, later this year, we will select a collection of compounds that we will basically move through the last tinkering, the last optimization spiral that I was talking about, in order to make that final selection. Preclinical trials are the last stage before clinical trials. These are government-mandated, basically safety studies in certain animal models. You have to do that in order to get permission to start a clinical trial. So this is a key step. You have to come up with a number of compounds that at least you think have a maximum chance of success, of passing through those final stages and then getting into clinical trials, which is exactly what we're doing. The amount of work that we're doing, that I tried to explain, a bit in this presentation is all intended to achieve that purpose, to come up with a collection of compounds, not just one, but a collection of compounds that have the maximum chance of ultimate success. And of course, the really big thing is the start of human trials. So that's the timeline along which we work, and those are the most important key milestones for us in the near future. At the bottom you see clinical biomarkers. That builds on what I told you a little bit about real-world data studies. But not only that, we're doing other work as well, in order to make sure that once we're ready for our first human trial, we will not be blind. We will have tools to measure the effect of our compounds.
Thank you. Thank you, Otto.